lesson is about electrolytic cells. And so these are not spontaneous. They are not going to happen without outside intervention. But if we have a source of electrical energy, we can then use that to convert it into chemical energy, or we'll convert that electrical energy to chemical energy. And so we're going to be passing electricity through an electrolyte, which is a substance that doesn't conduct electricity when solid, but does conduct electricity when molten or an aqueous solution. And during electrolysis, it will be chemically decomposed. Okay, something that doesn't conduct electricity as a solid, but does when it's molten or aqueous. We are talking about an ionic compound here. Okay. So, one of the big reasons why electrolysis is such a big deal is that we are able to get the neutral elements from their ionic compounds by discharging the ions or removing their charge through redox reactions. And so we can use this for a whole variety of things. We'll see that in a little bit. But if we want to get a pure element out, this is a good way of doing it. Okay, so there's a few components of the electrolytic cell. The first is our source of electric power, like, say, a battery. And you'll see it in diagrams as two parallel lines. And the longer line represents the positive terminal, and the negative is that shorter terminal. So electrons are going to come out of this short guy and go in from our whole circuit to the long guy. And I remember that this is positive because if you deconstructed a plus sign and stacked them on top of each other, it would be longer. Okay, our electrolyte, we already talked about what that was. Our electrodes, these are going to be something that conduct electricity and are submerged into our electrolyte. They'll be connected to the power supply. They're not going to touch each other because that would complete the circuit without our electrolyte being involved. And these are going to be made of some sort of conductor, frequently a metal or graphite. And then we'll have our wires that connect the power supply to the electrodes, and of course those will not be submerged in our electrolyte. We'll actually use our electrodes for that. Okay, so here's the big idea. Here's our battery. The power source is going to push electrons out from the negative side and into this electrode. Okay. Well, this electrode will be relatively negative. Okay. Meanwhile, electrons are getting pulled out of this electrode, so it's relatively positive. Okay, well, we know that opposite charges attract. So here we have our electrolyte that's filled with anions and cations. The positive cations are attracted to those negative electrons, and they are reduced at the cathode. Meanwhile, the anions are attracted to the anode, where they are oxidized. Okay. And so in your notes, you have what happens at the negative and positive electrodes. Now, if you picked up on this, oxidation still occurs at the anode, and reduction still occurs at the cathode. But the relative signs are flipped now. So the anode is now positive and the cathode is now negative. So your whole anox red cat mnemonic device, that still works. Remembering the charges, you got to remember that they're flipped. Okay, so let's look at a real life example of how this goes. Okay, molten sodium chloride. We're going to draw and label this. So we're going to start with our graphite electrodes, and they're submerged in molten sodium chloride. So molten, meaning liquid, by the way. Okay, we're going to hook up our battery. And the electrons are going to come out of the negative side and get pushed into this electrode, which then means that it's negative and this one is positive, so cathode and anode. Our sodium ions are attracted to this, and you see here's our reaction for it. They're going to be reduced. Okay, so red cat, reduction at the cathode. And you'd actually see solid sodium start to form here. So sodium is a kind of silvery metal. On the anode side, or chloride ions are going to be attracted. They're going to lose electrons and become diatomic chlorine, so Cl2, and you'll see yellowish-green bubbles being produced, a yellowish-green gas. So here's your half reaction here. Notice that the sodium could be balanced of just sodium plus 1 electron, but we've got to have it balanced, so 2 electrons gained, 2 electrons lost. And so your net reaction would be 2 sodium ions, liquid, plus 2 chloride ions, all liquid, yielding liquid or solid sodium, depending on the temperature if it told you specifics, and chlorine gas. So if you're wanting to purify or get out pure sodium, this is the way to do it. All right, let's try writing half reactions for a few salts. And I'm going to go ahead and talk about the observations that you would see just to remind you of some of the properties of elements that we've dealt with in terms of characteristics that we associate with those. All right, so we've got potassium bromide. At the anode, we'll have our anions attracted, and they'll be going oxidation. So our anion is bromine, and it's negative. So Br with a -1 charge, and it's liquid, and it's going to form liquid diatomic bromine, and then there should be a little plus sign, plus 2 electrons. Okay, so here's our oxidation reaction. Remember that fluorine and chlorine are gases at room temperature. Bromine is a liquid, and iodine is a solid. So if you're not told a temperature and like melting points and something like that, just go with the states that you know they are at room temperature. Okay, at the cathode, we would have potassium. The cation is attracted to the cathode. And we would have liquid potassium ions forming solid potassium. So there's our reduction. Okay, let's talk about observations. If you think about what we've discussed, bromine is kind of an orangey brown. Oh, by the way, there's your net reaction, just FYI. And so you would see an orangey brown liquid at the anode, and potassium is kind of silvery, and it'd be a solid at the cathode. Okay, same song, second verse. Magnesium fluoride. Again, our anions are attracted to our anode, and they are oxidized there, so fluorine forms. At our cathode, we would have magnesium form. So our net reaction, and that should have charges. This should be Mg plus 2, by the way. And then observations. Fluorine is a pinkish orange gas, and magnesium's a kind of silvery solid. You've seen that before, like magnesium ribbon. Last one, I want you to try it on your own. Don't worry about observation just yet, but write those reactions and then check your work. Okay, so here's what we should have gotten. And the overall reaction, again, that should be zinc with a plus 2 right there. Observations. Sulfur is a yellowy powder, so you'd see a yellow solid. And then zinc is still silvery. So what do we do with this electrolysis other than purify elements, say like from their ores or from their ionic compounds? Oh, sorry, forgot about this one. This is a close-up of tin chloride being electrolyzed. So here is the tin, SN, being formed on the cathode, and the anode has chlorine gas being formed. You can see that kind of yellowish green. So I thought that was a pretty neat picture. Okay, our other big application for electrolysis is electroplating. So we're depositing a layer of one metal on top of something else. And so you can draw this for your setup. Here's the big idea. You have something that you want to cover up, say an iron spoon. And you want to cover it in silver because it's a lot cheaper to pay for a spoon with a thin layer of silver on it than something that's pure silver, right? Okay, so you've got your object to be plated, and then you've got a pure sample of whatever you want to plate it with. So in this case, silver. And you've got your electrolyte, which contains silver ions as well. So say silver nitrate, aqueous silver nitrate. Well, we hook it up to a power source, we flip the switch, and electrons get pushed in here. So this is our cathode, and that's going to be the site of reduction. Well, the silver ions that are in this solution are going to be attracted to it. They're going to gain their electrons, and they're going to start to cover this spoon with silver ions. Meanwhile, our anode is the site of oxidation, and so these silver atoms are going to lose electrons. The electrons are going to go up and into the power source, and the atoms are going to go into solution as ions. So we're replenishing our source of ions, and you'll see the spoon start to get covered with silver, and the anode will actually get smaller. So why do we do it? Again, one is to make nice, pretty things, especially to do so somewhat inexpensively. A more practical utilitarian, corrosion control. We galvanize iron, or we cover it with zinc. Zinc is higher on the activity series than iron, so zinc will be preferentially oxidized, or it will be a sacrificial cathode. It will react with the oxygen to form zinc oxide, but the core of the structure is still iron and maintains its structural integrity. And then also, sometimes you can do things like this. You can put chromium on top of steel, and it reduces the wear on tools. So there's a lot of different reasons for electroplating things, but those are some of them. And there you go.